So let me explain what we are looking for here. We are looking for the total electric field radiating by this small aperture, and this will be the sum of two electric fields, E1 plus E2, where E1 is generated by the electric current K is radiated, and E2 is radiating by the magnetic current. And now E1 was pretty simple to explain, except for a small detail, except for this theta x. What is theta x? Let me make a drawing here to explain this thing. So, if I redraw the Cartesian coordinate system, x, y, and z. Now my current source is actually in the x-axis. This is of the length delta y, and the current actually flows in this direction, I, and the h is delta y, okay? But because this thing is in the x-axis, now to find the electric field at a particular point in space, so say this point is up here on the distance r with the electric field here, whatever it comes out, E1, out of my calculation. I do not use this angle theta here, but I have to use the angle from the actual polar direction. And the polar action is this theta x here. So this was the standard theta I had here, and this theta x has to be measured from the x-axis because the current flows in the x-axis. That's the trick. Some things can cancel out here. Like this is a 0. This cancels out. So this simplifies our life. Now, the other question is how to get the radiation for the magnetic current, for the magnetic dipole. For the magnetic dipole, we could develop the same equations we developed for the electric dipole. But since this magnetic current does not exist, we didn't do that. But the trick is to compare equations. We know that the magnetic field generated by an electric current, only radiation only, I look at, is 1 phi here, is jk over 4 pi, I times h, e to the minus jk r over r sine theta. Now making a comparison with the dual example, this is a dual example having the magnetic current. With the dual, its dual example is electric field generated by the magnetic current. So it's also approximately 1 phi. 1 phi. It's also jk over 4 pi. It is also magnetic currents times h, e to the minus jk r over r sine theta. And because of the additional minus sign in the Maxwell equation in the Faraday law, we also have a minus here. The only difference is this minus here. But electric current generates magnetic field, magnetic current generates electric field exactly in the same way. All the equations would turn out exactly the same, except for this minus sign that we start with already from the Maxwell equations. So we could now write down the magnetic field radiation. And this will be E2. radiation from the E2, the radiation from the magnetic field, is now minus 1 phi. Jk over 4 pi. Then we have E magnetic here, E magnetic times h, e to the minus jkr over r, sine theta. But we have to be careful. Why? We have to be careful because now where is this magnetic current oriented? I should redraw here now this drawing here. For the magnetic current flows in yet another direction. So if I remake the drawing here, the magnetic current is actually here in the y-axis. The length is delta x. So this is x, y, and z. There is our radius vector r, to the point where I'm going to calculate the field E, E2 here. Now, which is my axis? My axis is axis y. So I have here now theta y angle, and I need to make the projection of this r to the zx plane. And this makes a projection here to the zx plane. And for this projection, here I measure the longitude in the zx plane. This is phi y. So, to complete this equation, this should be phi y, because the current is flowing now. The magnetic current, here, I forgot magnetic. The magnetic current is now flowing in the y direction. And here I should have theta y. I should be very careful about these angles. Should be very careful about these angles. And now let's look to the quantities. Here I have to the quantities. H is now what? H is now delta x. The length of my magnetic current is delta x. And the magnetic current itself is what? Is K magnetic here times delta y. K magnetic, the magnitude of K magnetic, times delta y, and there is a minus sign in front. There's a minus sign in front because this current is flowing in the opposite direction, minus sign. So to rewrite now the result with the new quantities, E2, what is equal to E2 is now equal to minus 1. And not minus, plus, because I have minus here and minus here, they give plus out. 1 phi y, jk over 4 pi. K magnetic, I can express it is exactly equal to E0. E0. E0 without the absolute sign E0. Delta y, delta x. Oh, sorry. No, delta y here. Oh, I made a mistake. This is delta y is the length in the y-axis, so this is delta y actually. This is delta y. This is delta y. I made a mistake here. I have to correct. This is delta y, and delta x is the width of this current. Delta x is the width in the axis. See the width of this current is delta x. Delta x. I mixed up delta x and delta y. So here is now delta x, delta y. delta y e to the minus jkr over r sine theta y. So, comparing now, I have to sum this and this. This is what the electric current is radiating. This is what the magnetic current is. This is the discontinuity of the electric field, of the magnetic field radiating. This is the discontinuity of the electric field radiating. So if I make this summation now, what is the total electric field? The total electric field radiated by this electromagnetic Huygens source. Only this is different and this is different. So is minus 1 theta x sine of theta x plus 1 phi y sine of theta y, and this is what is different in both expressions, and all the rest is the same. All the rest is jk over 4 pi. This is present in both equations. It is E0 on both sides, so the initial plane wave, the electric field on the Huygens source. The corresponding magnetic field, we assume that it's related as in a plane wave. Delta x, delta y. Delta x, delta y, this is actually the size of my Huygens source. The radiation term, e to the minus jkr, the delay divided by the distance. And the geometry is all in here. So we got the result for the electromagnetic current source, where delta x and delta y are much smaller than the wavelength. We should be careful about this because if we really make such a source, such a small aperture in a screen, there will be also edge effects on this currents flowing on the screen, edge effects. So this is only useful as in the same way as the current segment we had, it had charges on both ends. Here we have currents in the screen. So this is only valid when we integrate this over the whole surface. And that's what we intend to do. What we want to do is to integrate this over the whole surface, over the whole aperture of what we have. The only issue, the only open issue is this complicated geometry inside here. But this complicated geometry, what does it really contain? Okay, it contains trigonometric functions of the angles we have, various angles. And we have two unit vectors that are both in the theta phi plane. They have no radial components. This has no radial component. This has no radial component. So their sum will also have no radial component. Now, calculating this thing, how can we solve this thing? We have to convert everything to x, y, z coordinates. X, y, z is the same for all three spherical coordinate systems. And we have to compare the result. It's a very lengthy calculation, about 1 hour of work on the table, and I do not have this hour to do this calculation. So I have to write the final result. Maybe I distribute this usually to the students, but I didn't do that today. So this is the whole calculation we have to do on the board to prove what this is. And actually it's not that complicated. I will rewrite it here. Just. This is identical to, okay, so now this is 1 theta cosine phi minus 1 phi sine phi. It is not all, it is 1 plus cosine theta. This is this expression rewritten in just a single spherical coordinate system with the north pole in the z-axis, so the standard one. The standard one. And then we have everything else that's left. Jk over 4 pi E0 delta x delta epsilon e to the minus jkr over r. And all the directional components, so theta and phi, we have them in front. So what we can see, what are these terms? This is just a unit vector. So you see, if one vector orthogonal to another, one has cosine and the other has sine of the same angle, they sum up into a unit vector. So this is polarization. And this thing here is the actual radiation pattern of our Huygens source. You see that the electromagnetic Huygens source is not really a perfect point source. It is a point source, but it has some directivity. It has some directional properties. It also has a small directivity, quite small, around 3 directivities. Polarization. Where does the polarization, where does it point? When we are close to axis z, so when z is much smaller than x or y, then the cosine of theta is also very small. And if the cosine of theta is very small, then this thing simplifies to 1x. So the polarization is, I could write it here, it's maybe easier to understand. If I write this minus 1x, if I write it here. So the polarization is around minus 1x, close to the z-axis. So the Huygens source really does not change the polarization, does not affect the polarization at all. But we need this complicated expression because 1x is okay on the z-axis. But 1x anywhere else also has a radial component. We know that radiation may not have a radial component. There are no longitudinal electromagnetic waves. The Maxwell equation prohibits that. So we have to account that these things turn as we move around the space to avoid any radial component. That's the reason why we cannot write simply minus 1x here. But close to the cosine theta is equal to 0, this expression is very close to minus 1x. So there is nothing special. And of course, we have some proportional constant. We have the thing is proportional to the amplitude of the plane wave coming to the aperture. It's proportional to the size of the aperture. It has the standard radiation term, delay e to the minus jkr divided by the distance. So this is all very, very, very standard. Well, there is yet another thing that's still bothering me here. And this is this magnetic current. We cannot make that one. Okay, it's just a mathematical replacement now. It cancels out of all equations. You see, here we have E0 only. It's just to replace the jump of E0. A jump, in reality, we don't have this jump. But still, it bothers me to have in the equation some unphysical quantity, and this is this E, this I, this current of magnetic charges. We don't have this. This does not exist. It's just a mathematical help here, but still it bothers me that it does not exist. But on the other hand, we had the equation for the small loop. The equation we had over there was E was just the radiation term, 1 phi, the direction, k squared z0 over 4 pi. Electric current, I will call it I2 now because we are in the for this component here, times surface of this loop, e to the minus jkr over r sine theta. You see that with a small loop, we can generate exactly the same field, exactly the same jump as we can generate with this strange magnetic current. If we compare the terms right now, so if we're comparing the terms, what happens? So minus jk E magnetic times h should be equal to k squared z0, this I2, the area of the loop. If we replace our inexistent magnetic current, magnetic dipole, with a real-world magnetic dipole, a small loop is a real-world magnetic dipole. We can do it with real physical quantities. We could just calculate now the required quantities we have here, the required quantities, so we can cancel out one of the k's. This k we can cancel it with this square here. So we get the equation that our I2 times A prime should be now equal to what? To minus J E magnetic times H divided by K Z0. So we have now the tool how to replace this strange magnetic current with real-world quantities. Now, what is the physical realization of Huygens source? If someone comes to you and tells you, I want a Huygens source, please build one for me. What are you going to do? And now let's make a drawing of this new strange device. And I should write now to, since my board does not have 3 dimensions, I draw the axis y pointing out of the board. So this is axis z, this is axis x. What do I have here right now? What do I need? I need a current element or electric dipole that's I1 times flowing this direction times H. And I need a magnetic dipole, a small loop that has its axis in the y axis. The axis of E magnetic was in the y axis. But that's why the loop has now to stay in the in the xz plane. This is the loop with the area A prime and with the current I2. Now, please don't ask me for the sense of the currents since there is J in between. So they are in quadrature, these two currents. But what do these two? So this one, I1, generates E1, and E1, points here, E1, and E1 also points here. On both sides of the current element. They should be also the same length. Sorry, I didn't draw them separately. But where does I2 point? I2, here it generates an E2 in the same direction, and here it generates an E2 in the opposite direction. So the two, the electric dipole and the magnetic dipole, their field sums in the plus z direction. In the plus direction, I have 1 plus cosine theta. This when cosine theta and go cosine theta goes to 1. Sorry. Cosine theta goes to 1. Theta goes to 0. Cosine theta goes to 1. This I made a mistake before. Sorry. When we have small theta in the plus z direction, this is equal to 2. We have two components of the same size that actually sum up to a double field. In the minus z direction, our theta, cosine theta is minus 1 because theta goes to pi, cosine theta goes to minus 1. 1 minus 1 is 0, so these two cancel out in the minus z direction. So actually the radiation pattern of Huygens source looks like this. This is f of theta phi, and this is theta. Goes from 0 to p to p half to p. P here. We start with 2, and this is now such a function. Or drawing this in 3 dimensions, I have still some space here. If I draw the z-axis here and I draw the rotation symmetry metric pattern in the x and y axis, so to make a polar diagram, the radiation pattern of the Huygens source, if I draw it here, it's something like this. Mathematicians call this a cardioid, f of theta and phi, though it does not depend on phi, is rotationally symmetric. So to learn what now my Huygens source is. This is the theory behind. Now we have our main result. Our main result is this thing here. This is usually simplified. Look, we prefer to use the wavelength rather than the wave wave number here. Rather than the wave number, we prefer to use the wavelength. So the wave number is simply 2 pi over the wavelength. Usually we draw this with a wavelength. So if I rewrite the result here, I think I can erase now this picture over here. So to rewrite everything, now the radiated electric field is, the polarization is 1 theta cosine theta minus 1 phi sine phi. And this is almost the same polarization as the original wave that illuminated our aperture. It's almost approximately, so let's draw it here. This is an approximation to 1x, but it's the exact solution, considering that the radiated field should never have a longitudinal component. Then, this jk over 4 pi, this is j over 2 lambda, if we replace it with lambda. It's the electric field on the aperture. Okay, sorry. The electric field on the aperture is 0, and we have delta x, delta epsilon, the size of this Huygens source. We have e to the minus jkr over r. This is radiation, so delay and inversely proportional to distance. This is always true for radiation. And we have the radiation pattern 1 plus cosine of theta. So this is our final result that we have, as usual, that we have the right first, polarization first, radiation pattern last. strength of our source, some physical constant in between, and the radiation constant. We rewrite it, everything in this way. Now, what is left of this hour, we could see what happens if the polarization of our Huygens source is not 1x, if we have a different polarization. If we have a different polarization, what happens? So, redo all this drawing once again. So I have to erase everything here now, and if you can still see anything on this board.
There a small mistake down there. One with the on the bottom under polarization is the 1x left.
Yeah.
Left. More to the left.
Left where?
Polarization is approximately 1x. The term that under there is 1 theta cosine phi, which should be probably 1 theta cosine theta.
No. Should be phi. Should be phi.
But then the upper right formula is wrong.
Maybe I messed up with some other formula.
Yeah.
Okay. This is phi. Sorry. That's the mistake. This is phi. There is always phi in here. There is always phi. I made the mistake here. Here was the mistake. Theta in place of phi. This one is correct because you have to have cosine and sine of the same angle so that these two can sum up. These two are orthogonal. They can sum up in a unit vector. And the unit vector they sum up is close to 1x, close to the z-axis. If you go from the z-axis towards the x-axis, this is 1 and this is 0. So it's 1 theta. 1 theta is approximately 1 phi. But if you go from the z-axis towards the y-axis, sine is 1 and cosine is 0. So 1 phi, if 1 phi points this direction, but 1x points the other way. So that's the reason for this minus here. You can immediately check it where the sine comes from. But of course, this should be always angle phi, not theta here. The angle should be phi. Thank you for noting the mistake. Okay, now the issue we want to explore here is what happens if the polarization is different. We only solved our problem for the polarization 1x. What happens if my plane wave coming to my Huygens source, I will redraw this thing, probably trying not to cause that much clutter on the board. So we have here the aperture is delta x and delta y. But now we have our plane wave that's directed in the y-axis. So x, y, and z. We want to explore the other polarization. So electric field now is equal to 1y times E0 times e to the minus jkz. This term will vanish when we come to the xy plane. What is the corresponding edge? The corresponding magnetic field should be minus 1x. So the corresponding this was E0, H0. E0, H0. H0 now is minus 1x. E0 over Z0 if it's free space, e to the minus jkz. So this is a plane wave coming from free space to our obstacle, to our screen. On the screen here I have now electric field in this direction. Electric field E0. And I have magnetic field in this direction. H0. E0 and H0. What is now the radiated field at an arbitrary point in space? So this is R, this is theta. What is now here the radiated electric field? We can rewrite anything, everything will be valid except for the polarization. We have to turn the polarization by 90 degrees. How do we turn the polarization by 90 degrees? By summing pi half to all numbers here. And if I sum pi half, I obtain, so this electric field here, I obtain, again, it will be the sum of 1 theta and 1 phi. And all the rest is the same. All the rest is the same, so it's j over 2 lambda. It's E0. It's delta x, delta y, size of our Huygens source. It's radiation, jkr over r, and the same radiation pattern of theta, because this does not change. But here we have a change, and the change here is that this will be before we had this will be now if this we have sinus sine phi plus cosine phi. If we shift everything by 90 degrees, and there's a plus sign in between. So we can actually use the same formula, just turning everything by 90 degrees around the z-axis. That's all the difference we have. And if we want to go even more general, if E0 has an arbitrary polarization, so if E0 it's arbitrarily polarized, then we can also do a similar calculation, just combining both results. It gets complicated, but what is the issue here? With Huygens sources, next hour we are no longer going to deal with polarization. We know that polarization is preserved. Mainly it's maintained. It changes slightly when we get off axis, but that change is only required to remove any longitudinal component that's not allowed by the Maxwell equations. So if we have a field like this, so if we have E0 now is equal 1x times Ex plus 1y times Ey. This could be arbitrary polarization. What is now the result? Summing both things together. So electric field, the radiated electric field is now, the first term is for 1 theta cosine phi minus 1 phi sinus phi times Ex plus 1 theta sine phi plus 1 phi cosine phi Ey. And now everything multiplied by everything else, multiplied by j over 2 lambda, multiplied by the size of the Huygens source, multiplied by the radiation term, multiplied by the radiation pattern. So this all comes together. So in this way, we could actually solve the problem for an arbitrary incident electric field. Of course, this should have for a plane wave e to the minus jkz. This term vanishes on the surface. Without the dot, I don't want a dot product here. There are no vectors involved over there. So in this way, we could solve any problem here. Further on, we are not going to deal with polarization any longer. We know that the polarization mainly is maintained. This thing here is almost 1y. So yeah, of course, at small z, so at cosine theta going towards 1. At theta going towards 0, so in the proximity of the axis z. And similarly, it changes a little bit when we go away from the axis z to remove any longitudinal component. What do I want to show here is that the Huygens source actually does not depend on the polarization. The idea behind the Huygens source is independent of polarization, and next hour and also next week, we are not going to deal with polarization at all, because it does not play a role in the whole discussion. What we have to take care of, if we have a very small Huygens source and the screen around, all around, then we may have here edge effects, because these fields cannot vanish at the ends of my at the edges of my aperture in the screen. So the Huygens source is a very useful principle, provided that it really generates such a field. There are no currents flowing in the screen. If there are currents flowing in the screen, then we have problems. Also with this antenna, like here, yes, there are small currents wrapping around every edge here, and also here there is some radiation here and some radiation here because of these currents wrapping around here. But as long as this thing is large compared to the wavelength to our waveguide, these currents are small. And we are going to neglect these outside currents. We are going to put here so many Huygens sources, one close to another, that we do not have this edge problem of this edge effect on the Huygens source. This is just to explain you that we can use the current source, the Huygens source, as is explained on this board. We can use it for all practical purposes. For very small apertures, it doesn't hold, because for very small aperture, if these two are really small and there is a conductive screen all around, there will be currents flowing in the conductive screen. If there are currents flowing, that means that there is radiation from the screen, from the conductive screen. So just to explain you where the limits are, it's not something, this was our simplification, and this simplification fits very well what we are going to do next hour. Fits very well in the problem. But in the real world, there are currents wrapping around the screen here and here and here and here on all edges. And if this is small, those currents are significant. If this is large, currents are insignificant, because most of the radiation comes out of the aperture, not out of the edges. So this should be for this hour. Next hour, we should see how to calculate the radiation now of a large aperture. No longer Huygens source, but large aperture.